Hey everyone, this is Brian. Welcome to week 7 of CSC 143. Hope you had a great weekend. Your exam 1 grades have been posted. Please check Canvas for a more detailed breakdown of how your grade was calculated. Overall, the class did pretty well. I think the median grade was around a B, which I'm pretty happy to see. If you didn't do as well as you thought you did, or if you didn't do as well as you wanted to do, I wouldn't fret about it too much. I think overall the class did pretty well, and in the future, you're going to have plenty of opportunities to make up for any points that you might have missed via bonus points and other opportunities. So I think everyone is generally in a pretty good state, and I wouldn't be too concerned if you didn't do as well as you wish you wanted on the exam. Overall, I feel like the class did pretty well, and you can check the exam. You can check the exam comments, and you'll be able to see the reference solutions that I had posted to those exam notes that you can take forward with you as you continue to study. Before we get into this week's topics, I want to talk about the reading that I had to do last week, which is the final of the 5 solid principles, the D in solid, which stands for the dependency inversion principle. And dependency inversion principle simply tells us higher level modules should not depend on lower level modules, both should depend on abstractions. We've talked about abstraction a lot in this class already. We've talked about how we can use interfaces, for example, in Java, or abstract classes to enforce that concrete classes, actual class definitions with implemented methods, must follow a specific specification such that clients of these classes are guaranteed to have these certain interface methods available. And the nice thing I like about this approach is that it explicitly separates what is the callable interface, the methods you can invoke on a class, versus the underlying implementation, the actual class that's doing the implementation. We saw a lot of abstraction in action in Project 1, actually, where I had you develop that world with using the collections and the hash map and the hash set and the kind of linked list or the array list or whatever other structure you chose to use in place of those interfaces. What this enabled you to do, and what this enabled other clients to do should they adapt your world, is that they can fulfill the required arguments of whatever inputs your program is taking, like with that restaurant and the recipes, with whatever underlying structure they see best fit suitable for that function. For example, rather than an array list, we could have used a linked list throughout the entire project. Is that the sensible thing to do? I don't know. I guess it depends on what client is actually fulfilling or is actually trying to use your program, as well as the kind of data manipulation that goes on with their underlying structures. But I think you get my point in that it doesn't matter what the underlying structure is, so long as it meets the functional requirements in terms of methods that those classes offer, that your function can then ingest and invoke on. I think the example in the reading also does a pretty good job of emphasizing this point of valuing abstractions over these concretions. One example they give you is this copy function that takes in a reader and a writer, where the reader is like this explicit keyboard reader, I think, and then the writer is like this concrete screen writer. And while it works, what we end up getting is a very strong binding between this keyboard and this screen, where really what we need is something that is providing keys, an input, and providing a means of sending to output. So what the reading suggests we do is instead, let's break this copy function up into something that depends on abstractions rather than concrete structures. Let's depend on a reader-like structure and a writer-like structure, so that so long as it supports a read and write-like operation, we should be able to reuse our copy function in the future with whatever concrete classes implement these read and write interfaces. Okay, that's a lot of me talking. I think that's enough for our intro today. This week is going to be really interesting. We're going to be covering trees and recursion, 2 of my favorite topics, and you'll be seeing a lot of applications of this moving forwards throughout the rest of the class and perhaps the rest of your computer science career. So do look forward to that. Do enjoy the video. Thank you. Hey everyone, this is Brian, recording another video lecture for CSC 143. In today's video, we're going to be learning about a new data structure, the tree, as well as recursion, a pattern that's going to enable us to write more powerful algorithms to traverse these more complex data structures. Recall that when we learned about the linked list, we were motivated to create this linked list structure by the restriction that the array list required that all elements be stored contiguously. The array list is of course backed by a primitive array. Anytime we want to expand and add elements to the array list, we have to copy all those elements over and move them to an array. When we came up with the linked list, we took away that restriction that all the elements had to be stored back to back, and let each element be stored individually in its own node instance that would then reference its neighboring nodes in order to form a chain of nodes that would form the list. Linked lists have this restriction that by nature, each node is going to have up to one successor next element. And this is what makes the linked list a sequentially ordered collection that is going to fulfill the list interface in Java. If we lift this restriction that each node in a linked list can only have one successor, the resulting structure is going to be a tree. A structure that's built out of nodes, where each node can have multiple successor nodes instead of just one. Let's take a look at what I mean by that. Up here on the upper left of the whiteboard, we see a basic linked list structure. We have a chain of nodes where the head node is designated as the start of the list, and each next field in each node is going to reference the successor node that comes after it within the list. The node class itself is a relatively simple structure. It's simply a generic type that includes a generic payload value and a reference to a successor node. With a tree structure, we're going to take away the requirement that there can only be one successor, one next field. In this example in the lower left, I show you what's called a binary tree. A binary tree has the same root structure, so that we have one node designated as the sort of head of the list, or head of the tree, or root of the tree in this case. We've got a same payload value, but rather than just one next field, I've designated a left and a right field within this node, such that the left field can point to another node, and the right field can point to another node. Each of those nodes can also have their own nodes as children of their own. One simple way we can represent this in a node class is to build out the same class that we had built for the linked list, but instead add additional fields left and right that we can use to fill in the two possible children that a node can have. A binary tree is not the required property of all trees. Not all trees have to have exactly two children. Trees can have any number of children per node. Here's an example of a tree node class that has an arbitrary number of children. In this tree node, we have the payload again, but we have an array list of references to other tree nodes as the child field. This is going to enable me to build a tree that has an arbitrary number of children per node, kind of like a tree in real life. I hope you can see how we've extended this basic linked list to build out this tree structure without too much added complexity. The binary tree node is perhaps the most natural extension, and we're going to be seeing binary trees a lot. This tree node with unlimited children is a bit more complex because we have another data structure built into the node itself. But remember, in Java, everything is a reference. So really, tree node is containing a reference to an array list that lives somewhere else, and the array list contains references to other tree nodes that those themselves will have payload values and lists of their own. Let's take a look at how this all works in action back at the source code. But before we actually get to that, I want to go over some formal definitions. Trees have a head node called the root, very much like the head node of a linked list. Nodes can have child nodes, but they're not obligated to. Nodes that don't have child nodes are called leaves or leaf nodes. With binary trees in particular, each node can have up to 2 children. They don't have to have exactly 2 children, but they must have no more than 2 children. A couple observations you can make off the bat when we look at these trees is the first that the tree nodes themselves are not sequential and have no natural sense of order. With a linked list, there by nature of being only one child successor to each node means that there is a sequential ordering to all the elements within the list. Trees do not have the same effect. We cannot simply say there's a canonical ordering to the leaves on a given tree. Instead, we have to navigate to each node and consider which path down the tree we want to go down if we want to traverse the tree. As a result, trees are not going to support indexing. It doesn't make sense to get the nth node of a tree because there's no natural ordering involved. Left and right does not necessarily dictate that we start left or right first and navigate the tree in a specific order. So what are some other ways we could use to identify nodes? One way we could do this is simply attaching unique identifiers to every node, but that seems like a lot of work. Another way we could do it is using the path from the root of the tree leading up to that node as the unique identifier for it. If we have a path of directions, kind of like directions in real life, going left, right here, taking a U-turn or something like that, then eventually from any starting point we'll reach a given destination. And we can identify those destinations based on the paths that we use to reach there. The big O of trees are naturally B to the D, where B is the branching factor and D is the depth of the tree. The branching factor is the maximum number of children per node. So for a binary tree, B is going to be 2, and D is the depth or number of layers there are inside the tree. One thing that kind of is scary here is that trees are naturally exponential. Binary trees naturally have 2 to the n nodes, or big O of 2 to the n nodes. We want to, of course, avoid having to traverse and search every single one of those nodes. That, of course, is going to always naturally run exponentially. So we're going to talk about algorithms like binary search to make that search more effective. We can think of singly linked lists as trees with just a branching factor of 1. Trees cannot have cycles. What about linked lists? Let me talk about trees cannot have cycles first. What this means is that a child node of any given node cannot ever point back to an ancestor node as one of its own children. Each tree's child can only ever point to unique children that don't point back to their older parents. Very much like a tree in real life. Linked lists, on the other hand, technically don't have this restriction. We could absolutely build a circular linked list, as it's called, where a node in the list points back to a previous node already in the list. Arguably, doubly linked lists are just like this. A previous reference is going to take you backwards from the respective point of a next reference. Trees can be unbalanced. What are the consequences of that? When I say unbalanced tree, I mean a tree that has many nodes heavily weighted on one side or the other. Imagine a tree in real life where, for some reason, the branches always grow out to the right side but never the left. What you'll have is a tree that has many leaves and other branches on one side of the tree, but not the other. The consequence of this is that sometimes searching that tree and traversing the tree can be very costly, because the outcome is that we're going to have to reach very deep depths to go find whatever we're looking for. This is kind of like if you gave someone directions and took them down hundreds of miles down a highway versus just having them search nearby. Perhaps the amount of area traversed is the same, the content that is the amount of places being navigated to is the same, but one of these is a bit more costly than the other when it comes to looking for things, depending on the strategy we're using to search the tree. Now let's take a look at the code that we present on the whiteboard in action with the binary tree node and the tree node classes. The binary tree node is of no surprise to us. It's a generic class that has a left and a right field, very much like the next field in the list node, and a payload field. I've provided some simple constructors. A binary tree node constructor that has a payload argument simply assigns the payload and leaves left and right to be null. And then a binary tree node constructor that has a payload and a left and a right binary tree node arguments that we can use to conveniently assign those fields. Tree node is going to take that to the next level and offer us an arbitrary number of children instead of just at most 2 children. It's yet again a generic type. We have a payload field, but here, rather than just having a left and right field, we're going to support an arbitrary number of children nodes attached to this tree node by packing them inside an array list. We start out with a basic constructor that simply takes a payload and then forms a child list that starts out as empty. We can also supply that child list directly in the second constructor here. I've tagged on some methods, addChild and getChild, where addChild and getChild are going to go add children onto a particular node or retrieve an index of a child that is already on the tree. Now when it comes to actually assembling these trees instances inside our code, it's going to be a lot like how we built linked lists. We're going to construct nodes, build individual node instances, and then we'll attach them to each other using the references that we've provided within each class, like the left and the right, or the addChild method. we'll start out with a binary tree test. At the very top here, I've got this construct test that builds a new root field with simply a node that has a payload of 0. Then, much like how I assigned neighboring references to linked list nodes, I'm going to assign the left and right fields of this binary tree node with new instances of nodes that have 1 and 2 as the payload values respectively. The effect is that we have a root reference that points to this binary tree node with a payload of 0, and then this node itself has a left field that points to a binary tree node that contains 1, and a right field that has a reference to a binary tree node that contains 2. I can then, of course, look up the values within the tree, just like how I looked up values within the linked list. I can refer to the payload field of the root, which is, of course, going to contain 0, then the payload field of the left side of the root, which is, of course, going to contain 1, and the payload field of the right side of the root, which contains 2. So again, I want to emphasize that the tree, the structure, is built no differently than how we built the linked list. All we end up doing, in addition to what we had done with the linked list, is to assign a new node that is also attached as a second child to these binary tree nodes rather than just one next node that we saw with the linked list. Let's add a little bit more depth to this tree. We'll build out the same basic tree structure that we saw in the previous test, 0, 1, and 2. But then we'll go ahead and extend this tree on the right-hand side of the root by adding grandchild nodes 3 and 4 to the child of the 2 node. The 2 node is going to be root.right, and then by nature of root.right itself being a binary tree node, I'm allowed to look up the left and right fields of that node. I'll go ahead and assign those to 3 and 4. The outcome is that we have the same root node of 0, left and right children of 1 and 2 respectively, and then the 2 node, the right child of root, is going to have its own left and right children of 3 and 4. Then, just like with the linked list, I can use a bit of dot notation to look down this chain of references and retrieve the values inside. Root's right side has a left field that has a payload value. Remember, root itself is a binary tree node. Root.right is a reference to another binary tree node, which itself has a reference left inside it that points to another binary tree node, which of course has a payload field attached to it. Same story on the other side. If I go to the right of the root, I have a binary tree node. I can look at its right field to get to another binary tree node, and then examine the payload field to get the value of 4. Okay, now let's talk about how we actually can use algorithms to traverse these trees rather than doing it by hand as we saw. Here's a function called getIntegerAtPath. The JS doc, or the Java doc that I've written above it, is going to explain what this method does. It's going to retrieve the integer at the end of the path described by an array list. Let's talk about this path argument first, which is the second argument to getIntegerAtPath. Path is an array list of strings containing right or left directions from the root node. The first argument is going to be the root of the binary tree, which should contain integers. And finally, it's going to return the value that's at the end of that path. So this is kind of like in real life if I told you to walk down this street, take a left, go down this way, take a right, and tell me what building is at the end of that destination. We're going to do the same thing with a root node for a binary tree and a list of directions that have the string right or the string left inside. Here's how I'm going to do it. Let's go ahead and use the for each loop to iterate through all the elements within the array list, the path, and we'll retrieve the directions inside as this string D here. Then we'll ask, well, is the string equal to left, in which case I should push my root over to the left side. Otherwise, it's of course going to be right, so I should put my root over to the right side. Remember that Java is passed by value, but Java is also passed by value by reference. So root is a reference to whatever the original root was, but this reference itself is a copy. So it's okay for me to reassign those copies, and I won't affect the actual root of the tree. That is still going to exist elsewhere. So over here, I'm updating my copy of the root such that it's going to point to its left side rather than just itself. Then when I exit the loop and go back to the top, sorry, I don't exit the loop, I continue on the loop and go back to the top, I follow the next set of directions. Now my root is in a new place, and then when I refer to the root's left or right fields, I once again push my root forwards and update my root reference to point to yet another deeper node within the tree. This is very much like how we traversed the linked list. We would write a function like get for a particular index, and we would loop through all the nodes within the linked list by doing something like head equals head.next in order to push that head pointer forwards. With the root node, we're simply doing the same thing by reassigning it to whatever its left and right fields are, so that next time we enter the top of the loop, we reference this deeper node within the tree. Finally, once I've exited the loop and I've exhausted all the strings within this path list, I can retrieve whatever payload field is at the root that I've found. Now let's take a look at how that works. Here's my integer path test. Let's go ahead and build out that tree that I showed you earlier with 0 at the root, 1 and 2 as the left and right children, and 3 and 4 as the left and right children of the right side of the tree. We'll start out with a base case of the empty path, where I have nothing within this path. And then I can try and retrieve whatever's at the empty path, which is, of course, going to be the root node that has a value of 0. Next, I build a path that simply tells the user to go left. And then I see my get integer at path returns the value of 1, which is, of course, the immediate left child of the root. Next up, in my two-step path, I'm composing a path of just right and left, and I see that relative to root, going to the right and then going down the left is going to get me the integer with a value of 3. The use of strings as directions in our algorithm is a little bit suspect. You can imagine an array list of string being passed in here, where the path itself actually contains gibberish. It's not just left and right, it's arbitrary strings like letters and characters that are not just left and right. We can absolutely ruin that within our test suite, and the compiler is not going to complain, because of course, these types are still indeed strings. So that's one problem with using strings here. The other problem is perhaps a bit more philosophical, which is we don't need the raw string right and left in order to represent the directions right and left. Really, this is just a binary value. Either you go right or either you go left. It's 0 or 1. But here we've gone ahead and used up at least 5 bytes to say RIGHT and at least 4 bytes to represent LEFT. So there's actually 2 problems that I have with this array list of strings of paths, which is that these strings could potentially not be valid directions, and that these strings are arbitrarily and unnecessarily large. Now, there is one great convenience to using strings here, which is we can see as programmers what the actual values are. If I see a path that contains the literal string right and the literal string left, then hey, I know what it means just by nature of looking at it. But I do have these extra cons. The fact that it takes up additional space because it's literally a raw string here, and the fact that I can make mistakes and have a path composed of strings that are not actually directions. So how do we get around this? And as a small detour to this presentation, I want to talk about this language feature called an enum. An enum is like an integer with a name. An enum is a programming-only construct that lets us use labels disguised as integers, where the underlying integer doesn't matter as much as the label itself. We could have just used 0 or 1 for left and right, but then we could potentially forget what 0 referred to and what 1 referred to. What an enum is it's going to attach a label to these numbers and actually use numbers underneath inside the program for space efficiency. Here is an enum direction. Direction has 2 fields, left and right. I can visually identify the fields by their names, left and right, just like I visually identified the strings left and right. But what the compiler is actually going to do for us is it's going to replace left and right when we use them as 0 and 1, or 0 and 1. So it's more effective and more efficient when we actually run the program. Now let's talk about how we actually use this enum here. Here's my getValueAtPath function. Again, I have a similar function signature where I have a root node as my first as my first argument, and a path argument composed of a list of directions. So the first thing we'll notice is that direction acts very much like a custom type or custom class that we've just defined. Next, I can walk my list using the for each loop construct that we've seen before, and I'll pull out a direction of lowercase d out of these paths, and I'll ask if the direction I have equals the left direction inside my enum. The alternative case is that the direction is going to equal the right definition inside my enum. Let's talk about a couple things. The first is that I can use the left and right fields defined in my enum as if they were static fields defined on a direction class. And remember that static fields and static methods are essentially properties and methods that you can refer to based on the class definition instead of just an instance of the class. So here I can say direction.left because left acts like a static member of direction. At the same time, I can invoke the equals method on this direction instance. So what's interesting here is that direction itself is an enum, but I can invoke methods on it as if it were an object-like instance, as well as other methods that I would expect to see on an object. So I can treat enum instances as objects, and I can compare them relative to the static instances that seems to be attached to the enum definition. So here, if the enum d is equal to the left enum that's on my definition, I go to the left side. Otherwise, if it's equal to the right definition inside the enum, I go to the right side. And then when I'm finally done traversing my path list, I'll return the payload at the node I'm currently at. The clever thing about using enums here is that the compiler is going to enforce that the list that represents my path is composed solely of directions. And what we'll see in our test cases is that I'm only going to be able to refer to left and right inside my path. I can't just provide arbitrary values like I saw with the string version of the path. Let's see how that works. Here's my path test. I construct a tree with just the root of 0, left and right as 1 and 2 respectively, and then down the right side of the tree, 3 and 4 as the children of the right side node. Once again, I start out with a test of the empty path where I try to get the value relative to the root of going nowhere, which is the value 0. Then I build a path that has exactly one step in it, and that one step is going to be direction.left. Here I'm referring to direction.left as if left was a static member of direction, and left is going to essentially act like an instance of the direction class, or enum. Then I can pass in this one-step path to my getValueAtPath function, and discover that relative to the root, going to the left side gets me the value of 1. Similarly, down here, here's my two-step path composed of the enum fields right and left. And passing that to getValueAtPath relative to the root is that I get a value of 3. So the great thing about enums here is that I get the developer convenience of being able to quickly visualize and determine what these values refer to, which is right and left, but I also get the efficient storage of just having numbers in the backend and nice enforcement of these type definitions, where it's not going to let me try to insert something here that's arbitrary. This, of course, cannot be a string, because my array list is composed of directions. So Java is going to force me to either use the left or right values defined inside the enum. So in summary, I get the niceness and convenience of being able to visualize the values I'm trying to refer to, as well as the efficiency of just using plain numbers in the backend. Okay, now let's talk a little bit about runtime. Looking up an individual node in a tree requires us to walk the path that leads up to that node. Very much like how when we tried to use indexing in a linked list, we had to start from the head of the list and walk n number of nodes to reach the node we're trying to look for. So if a binary tree has n nodes, at most, in a worst case, we have to walk every single node to go find the one we're looking for, and the big O of lookup given a path is going to be O of n. However, this is a worst case scenario. This is what happens if the binary tree is unbalanced, and all the nodes are heavily weighted one side, and I get unlucky and the node I'm looking for happens to be at the very, very bottom of the tree. If the tree itself, if the binary tree was balanced, that is, roughly evenly distributed, then I actually get log of n performance. Remember that log of n is essentially the inverse of exponent. With a binary tree, every layer that I go down doubles the amount of potential nodes that can be stored there. If my tree is well balanced, that is, evenly distributed, then the depth of my tree is going to be limited to log of n. Let me give you an example. A tree with 1,000 elements, a binary tree with 1,000 elements, has roughly a depth of 10 if it's well balanced, because 2 to the 10 is going to be around 1,000. It's equal to 1,024. So that means, going down the path of my tree, at most I have to get to the bottom depth. Given a set of directions, I have to take 10 steps. Log of n to go reach the bottom of the tree isn't so bad. That's only 10 steps to essentially walk 1,000, or to distinguish among 1,000 nodes what node I'm looking for. Now, not every tree is a binary tree. This two-child limit is artificially imposed by our binary tree node class. We can always create that tree node class where we saw how every node is going to have an array list of children, which is going to permit not just a left and right field, but an arbitrary number of children attached to a given node. Let's go take a look at that class again. Here's my tree node class. I've got that payload field, but rather than just left and right, I have an array list inside, such that I can attach any number of children to a given node and use those to compose additional branches of my tree. Next, I'd like to talk about a problem that's similar to the tree pathing algorithm that we just wrote, but it's actually quite a bit more complicated, which is tree search. If we're going to search a linked list, it's actually quite simple. We just have to walk the list, examine every node, and look for the target value. Let's do a quick example in linked list test, just to drive this point home. Here in linked list test, I've written a method called indexOf, which is going to go find the index in which the value argument resides within the linked list represented by the root list node. I'll go ahead and start walking the list with this while loop and ask if the payload value at the root is equal to the value I'm looking for. If so, I'll just return the index which starts at 0. Otherwise, I'll move the root reference forwards by 1 and I'll increment the index. Eventually, I should find the value I'm looking for and return the index that I'm currently at, or I'll return -1. This is similar in behavior to any other indexOf function you might have seen in the past, such as a string character index1 indexOf or an array indexOf. I'll go ahead and wrap this method indexOf in a method called contains that's simply going to return the equivalent in Boolean form, where it'll simply ask whether or not the index is equal to or not equal to -1, which, if it equals to -1, indicates that the value is not within the list. Okay, so it's not too hard to figure out if a value is inside the list. We can quickly write a small test to verify that. Here's a simple linked list with the values 1, 2, and 3 inside, and then I can use my indexOf method to figure out that the value 1 is indeed at index 0, the value 3 is at index 2, and the value 999 is not present in the list. The contains method is simply a wrapper around the indexOf method, which is going to return a Boolean true that 2 is indeed in the list. Okay, so nothing too complicated. How does that compare to doing a tree search? Searching a tree for a target value is actually quite a bit harder. We no longer have a linear path to walk down. Suppose for a moment that we try to translate that contains method we just wrote using that while loop for linked list into this binary tree data structure. I've got a similar method signature with a binary tree node root argument as the first one and a value argument as the second argument. Then I'll start looping through my nodes. While the root is not null, I will ask if the root happens to equal the value I'm looking for. If so, return true. But then we have this interesting question of if the value I'm looking for is not presently at the root, but there are more nodes in the tree to search that are children of the root node, how do we decide which way to go? Do we look left or right? And if so, if we pick a direction, how do we back up if we happen to pick the wrong direction? Suppose for a moment that I did something like root equals root.left, but it also happens that the value we're looking for is not within the left branch of the tree. Then I have to back up my search somehow, but I can't necessarily do that, right? My binary tree nodes don't have references to their parents. They only have references to their successive children. And if you think about it, every time I make a step in the search, I have to make another decision between whether I want to search left or whether I want to search right. The effect is that we can no longer use linear iteration to search through all the values inside the binary tree. We kind of hinted at this when we talked about how binary trees don't have a natural ordering. And of course, this applies to all trees as well. We can't just necessarily index every single value from 0 to n because there's no linear order in which we can necessarily walk the tree. Searching a tree is closely related to several problems that require traversing all the nodes in the tree. Some problem examples include, how many nodes are in the tree? What are all the leaf nodes in the tree? What's the maximum value stored inside the tree? Iteration is not going to work for us here. We need a new strategy. And that strategy is called recursion. Recursion is a strategy for solving problems by finding a solution based on smaller instances of the same problem. Recursion involves two big ideas. The base case, which is the simplest subproblem we can try to solve, where the solution is trivial. For example, suppose we were tasked with determining if a value exists in a linked list, and the linked list only contained one value. That's easy. All we have to do is examine the root node and return true or false, depending on whether or not the root node has the value we're looking for. We don't have to search any more elements of the list because there are none. The second part of recursion is about the recursive case, where a solution to a complex problem is derived from a simpler set of subproblems. Extending that linked list example, determining if a value exists in a linked list can be determined by assessing the value at the present head node and then assessing the values among the rest of the list. Looking at just the value at the head node is like our base case. It's a trivial example, and all we have to do is verify one thing. Then, by nature of us having already figured out whether or not the root node contains the value, we can then decide whether or not to search the rest of the list. The rest of the list itself is going to be slightly smaller than the original linked list. So we've shrunk the size of the search space that we have, and we've made the rest of the problem simpler. The idea behind recursion is that we're going to break down our problems into several of these base cases and combine those results with these recursive cases that are simpler and simpler subproblems until everything ends up being the sum of several base cases together. Now let's talk about how we actually write these recursive algorithms. Writing recursive algorithms all follow the same process. These 3 steps here that I've outlined that I'd like you to remember. First step, write a condition that covers the base case. This will return exactly the solution to the base case. So for example, in that linked list search example, I have an if statement, simply asks whether or not the root node has the value equal to the one I'm looking for. If so, return true. Otherwise, write the recursive case that returns a combination of recursive calls to subproblems. What do I mean by this? Well, in a linked list example, the recursive subproblem is just the remainder of the list. Searching the remainder of the list, that is. So what I should do is I should return the recursive call to the remainder of the list and have that be my outcome result of this function call. And the third step is that we're going to pray that the recursive case works. And you'll see why in a moment that I like to have this praying step here. Let's go visit recursiontest.java to see some examples. Okay, so here's my recursion test file. And I'll start out with this function called getRangeSum. In the Java doc, you'll see that it's supposed to add all the numbers from 0 to I, where I have a single parameter I. Okay, here's my base case. The trivial case of I equals 0 just means I'd return 0. I don't have to do any more additional computations because the range from 0 to 0 is of course 0. Otherwise, it's time for me to write my recursive case, which is to break down the current problem into subproblems that are combined. So the solution to my current step, whatever I is right now, is going to be I. Then I can break down the remainder of the problem, everything else from I minus 1 to 0, by recursively calling getRangeSum again. This is where that praying step takes place. Here I'm combining the subproblem that I'm currently at, which is just this base case of the value of I, which I know I have to add inside my sum. I use the plus operator to combine this base case on the left with the recursive call on the right, where the recursive call is calling the same method again. But this time, the recursive call features a problem that's slightly smaller than the original problem I had. I started with integer I as my original problem space, and now I have I minus 1. The praying occurs because I pray that my recursive calls will eventually cause this I to shrink all the way down to 0 and finally hit this base case. And this is where the recursion terminates. Once I reaches 0, the solution will start to bubble up to these calls to getRangeSum, and then be added to whatever I value there are next to those recursive calls. Then those solutions will start to bubble up and bubble up and bubble up even more until I finally reach the initial call to getRangeSum, which is going to give me the sum of the numbers ranging from 0 to I. Let's see some examples as to how that works. Here's my range-sum test. I validate my base case is correct, getRangeSum of 0 returns 0, getRangeSum of 1 returns 1, and the getRangeSum of 5 is going to get me 15. 5 plus 4 plus 3 plus 2 plus 1 is indeed 15, and we can debug this to get a closer insight as to what's going on here. Let's go ahead and set some breakpoints at the base case and the recursive case and follow along. Remember that when you debug, you can click on this green icon, the green arrow, and click debug rather than run, and IntelliJ is going to pause execution when it hits a breakpoint. That is after it takes its time to compile. Okay, it looks like the first couple of calls to getRangeSum are actually occurring here. So I'm going to unset these breakpoints temporarily until we reach the third call, which I think is the most interesting one. I'll go ahead and hit resume, so I reach that point. Okay, I'm paused in this line. Now I'll go ahead and set some breakpoints in my base case and my recursive case, and then continue execution. Okay, so I start out with getRangeSum with a call of I set to 5, which is, of course, my initial call, getRangeSum of here, getRangeSum of 5. Of course, this does not meet my base case criteria, so I go ahead and step forward and reach my recursive case. Here I see that I is still set to 5, but then I'm going to be passing in I minus 1 to the recursive call to getRangeSum, and I'm adding that I is 5 to the recursive value here. So let's go ahead and click step in to go into the execution of this recursive call, and that takes me to the next step, which is one layer deeper, where I'm now calling getRangeSum of I of 4. Once again, I'm no longer at my base case, step in, I is now 3, not the base case, step in, not the base case, step in, not the base case, step in one more time, and finally I is now 0, which reaches my base case. So when I step over this conditional, I indeed start to return 0 here. Take a look at this frame section here in IntelliJ. The frame section is describing every single recursive call that we've made so far. And it's keeping tabs on all those base case values and what values to combine when we start to bubble up the return values from here on this line 23. Another way of looking at this is in my final call here to getRangeSum of 0, this is actually the 6th call to my function because I have 5, 4, 3, 2, 1, 0. When I return from this function, it's going to pass the return value of getRangeSum of 0 to the caller that had initially getRangeSum of 1. So when I step over, I'm going to step out, and then getRangeSum of 0 has resolved its value, and I'm going to add that with the call that had I of 1. Then when I step over again, getRangeSum of 1 has resolved its value, and I'm going to combine that with the I of 2. Step over, step over, step over, and this is actually the final call because I was 5 initially, and the getRangeSum of 4 value has resolved itself. I step over one more time, and I exit the test. So I hope that's given you a bit more insight as to how recursion is behaving. Our base case essentially guards against the moment when the arguments that we're passing into the function reach a point that's so trivial that we don't have to do additional recursion. Until then, we're going to keep hitting the recursive case and coming up with these recursive calls that once they eventually reach this base case, they're going to start resolving themselves and percolating and bubbling the values back up, combining them with the base case of the calls at the outset. Okay, let's look at another example. This function fib is going to compute the ith Fibonacci number. Our old friend Fibonacci is back to strike again, and we've learned how bad this implementation can be, but I think it's a great example of recursion because it's, again, a naturally recursive sequence. Okay, so Fibonacci has two base cases, I of 0, in which case I return 0, and I of 1, where I can return 1. I want to make this point here that it's okay to have multiple base cases, so long as they're all trivial implementations. You don't want to drag this on forever and have something like I is 2, 3, 4, etc., etc. You, of course, eventually want to make it recursive at some point. Here, my recursive case is fib of I minus 1 plus fib of I minus 2. This is where the praying comes in. I'm going to pray that whatever I pass into I here is eventually going to reach one of these base cases of 0 and 1. Okay, here I've got my Fibonacci test. Values 0, 1, 2, 3, 4, and 5, or indices, are going to get me 0, 1, 1, 2, 3, and 5, which is, of course, as expected for Fibonacci sequence. Fibonacci is naturally recursive, as we saw on the very first day, but it's also 2 to the n, which is pretty bad. It grows way too quickly for large numbers. Okay, check out this list contains implementation. We've talked about writing a linked list contains method and using iteration. This version is going to use recursion. I have a similar method signature where the first argument is a list node root and the second argument is the value I'm looking for. Let's think through our base cases. If the root is null, if it's an empty list, obviously the node's not in the list, or the value I'm looking for is not in the list. If the node itself is the only node in the list and there's no other elements, there's no other successive nodes on this linked list, then it's just a matter of whether or not the value I'm looking for happens to be this only node in the list. Then my recursive case is going to do something interesting. I still have to ask whether or not the value I'm looking for is at the current node. But if not, I'm going to defer the remainder of the solution to the recursive calls. So here I've got my base case of sorts. I'm asking whether or not the current value is present at the root node. And otherwise, if not, I will defer execution and have the solution to my subproblem be in the rest of my list. So just like how I implemented range sum, where I did so by combining a base case value with the solution to the rest of the problem, I'm going to do so here by passing on the rest of the list, which is the reference node starting at root.next, all the way back to the top of list contains, the recursive call. The outcome of that is that I'll ask whether or not the value is at my current head node, and then whether or not the value is at the rest of the list. And I'm going to pray that eventually root.next is going to be pushed forward to the point where it hits one of these base cases, like root.next is null, or the root itself becomes null. Okay, let's take a look at that in action. Let's test my base case. The null list cannot contain a value, so this should return false. Here is a list that has exactly one value. It does not contain 999, but it does indeed contain 0. Here's a 3-element list that I construct on the fly. Sorry, 4 elements, because I start with that same list node of 0 that I declared on line 88. I have its next neighbor be 1, then 2, and then 3, giving me a linked list of 0, 1, 2, and 3 inside my list reference here. Then I can see that my list does indeed contain the value of 3, but it does not contain the value of 4. We can debug these list contain methods, these list contain method calls, just like we had done with the range sum method. And I'll leave that as an exercise for you to try out on your own. Here's a similar example for linked list. This one's called get sum of list. Well, it's going to get the sum of a list of integers. Suppose I had a linked list of numbers. Let's go ahead and add all those together. I could very easily do it with iteration, but as an exercise, let's try it using recursion. Once again, I've got some simple base cases. If my list is empty, then let's return a default value of 0. If I only have one element in my list, then let's just return whatever values at the present node. Otherwise, I'll combine my solution in a very similar way to the other recursive algorithms we've seen. We'll take on the base case, the current value, and then add that to the solution to the remainder of the list, which is itself a smaller subproblem than the initial problem we were presented with. So I take my root value, then I add it to the solution to the remainder of the list, and I pray that the remainder of the list will eventually whittle down to one of these base cases here that will stop recursion and start to bubble up values that are going to end up resolving these recursive calls, which will combine with the base case, and then those calls will bubble up and return and resolve more recursive calls until finally I reach the initial call to my getSumOfList method. Let's take a look at how that works. I validate that the sum of an empty list is 0, the sum of a list with just one node is 0, that has 0 inside, and the sum of a list that has just 999 in it is equal to 999. Then I construct a list with the values 5, 10, 10, 25, and 50, which is going to get me 100. Once again, I recommend, if you have trouble understanding how the recursive process works, is go ahead and throw on some breakpoints and try debugging these tests on your own to see how the recursive calls will eventually translate into base case returns, and those base case return values are going to bubble up with these recursive calls here and start to resolve these recursive calls to combine them with these base cases and resolve the outer call. Let's check out one more. GetMaxOfList gets the maximum integer in the list. Similar method signature, I have a list node root, and I just want to explore the entire list to find the maximum value. Similar base cases, if I have an empty list, let's go ahead and return null. If I have a list with exactly one element, well, that itself, by definition, becomes the maximum value in the list, so let's just return that. Then we have to ask, how do we combine this base case, a list with one element, with the recursive case, a list with several elements? To decide between which of those solutions of the subproblems are the maximum, let's just compare them. I'll compare whatever root value I have with whatever maximum there is recursively for the remainder of the list and return whichever one is bigger. Here's how I'll do that. Let's keep track of the current value and keep track of whatever remains in the remainder of the list. So here is my praying step. I'm going to pray that my getMaxOfList method is going to find the maximum value in the remainder of the list. Then collectively, the solution to this entire problem becomes either the root's payload value or the maximum value among the remainder of the list. Whichever one is bigger is, of course, the maximum value among all the elements in the list. I'll go ahead and check. If rest is null, that is, there's nothing else at the end of the list, of course, the current should be bigger. Otherwise, if current, the value at the root, is greater than the remaining maximum, then I'm going to return the current. Otherwise, I'll return the rest. Here's my test cases. Empty list has no maximum. List with a value of 0 just inside has a maximum of 0. The list 0, 1, 2, and 3, the maximum value is of course 3 at the very end of the list, is going to have a maximum value of 3 when I call getMaxOfList. Let's make it a little more complicated. I'll append the value 9 to the very front of the list by making list be front's neighbors and then replacing list with this new front node. So I have the list 9, 0, 1, 2, and 3. Then I validate that indeed getMaxOfList gets me 9, which is the very front of the list. Let's do one more thing. Let's replace the middle value at list.next.next by assigning it to 555. And then I see that 555 indeed takes precedent over all these other values in the list and becomes the new max of the list. Okay, now let's take all these lessons we've learned and this pattern that we've followed so far for recursion to write a recursive algorithm for binary tree. Contains tree is going to ask if a binary tree contains a value. I've got a method signature that looks like the root, which is of course the root of the tree, and the value I'm looking for. Let's think about our base cases. If the tree is completely empty, then it's of course not in the tree. And if the root node that I have happens to convey the value I'm already looking for, then I can return true right away. Otherwise, I need to recursively look for the value among both of the children, left and right. If the value I'm looking for is in either side of that tree, then I can return true. That's how I'm going to combine my problem, is I'm going to ask, is it in the left? If so, return true. Otherwise, return whether or not it's on the right side of the tree. That's what I'll do here. My base cases will simply ask if the tree is empty or if the tree happens to have the value immediately. Otherwise, I will return contains tree on the left or contains tree on the right. Here's where the praying comes in. I've already resolved whether or not the base case has the value I'm looking for. If it does, return true right away. Otherwise, let's go look on the right side of the tree. I'm going to pray that my contains tree method works correctly and that root is eventually going to hit one of these base cases. The same thing happens on the left side. The value I'm looking for is either on the right or the left. So long as either one of these method recursive calls returns true, then my entire method returns true. One way we can kind of break this down is we can save the Boolean on the right or on the left inside these references to Booleans. Sorry, not references, these are actually just Boolean values of contains tree of root.right and contains tree of root.left. Then our solution to the overall subproblem, or the overall problem, the composite solution here, becomes on right or on left. As long as one of those is true, then the entire tree contains the value. Let's take a look at how that behaves in action. Empty tree does not contain the value. That makes sense. Here is a binary tree with the root of 0, left and right of 1 and 2, and then on the right side branch I'll have 3 and 4 underneath 2. Then I'll see that indeed the tree does include 0, 2, and 4, but does not include 5. One sort of neat thing about trees is that because they're naturally recursive, kind of like how linked lists are naturally sublists of other linked lists potentially, I can invoke the contains tree method on one of the sides of the tree as if it were a subtree of its own. So here root.right is a tree, and I can use it just like any other tree, just like root is being used in these previous calls. Just as a matter of review, let's go over this contains tree method one more time. I've got to start out with base cases. If the tree is empty, obviously not in the tree. If the root value happens to have the value I'm looking for, then it is in the tree and I can return true right away. Otherwise, I will form a composite solution to the remainder of my problem by asking whether or not the value is on the right side or on the left side. If either one of these is the case, then I return true. The clever thing about this composite solution is that contains tree of root.right, if that returns true, it's actually not going to search on the left side because Boolean operators like OR have something called short circuit evaluation. Java is going to realize that true on contains tree of right is going to make this entire expression be true, and it's not actually going to have to call contains tree on root.left. This is therefore slightly more efficient than saving the values outright, because Java knows it doesn't have to continue computation here. In any case, thanks to the combination of these two subproblems, I form a composite solution to the overall call of contains tree. The second and third steps are perhaps the most challenging part of recursion. Sometimes the subproblem is not immediately obvious, and making a mistake with a recursive call that ends up having the subproblems not actually be subproblems and not shrinking the values all the way down to the base case can result in an infinite loop. So be very careful when you start to write these recursive functions, and make sure that you're indeed actually cutting down on the size of the search space when you make those recursive calls, and that those recursive calls are somehow combined together to form a composite solution. Tree search is naturally recursive. Trees are naturally recursive. children are trees on their own that are a subset of the overall tree. So with the power of recursion, we can finally write our tree search algorithm. We've seen this in action. We have a base case asking whether or not the tree is null or happens to have the value we're looking for. Then a recursive case is going to form that composite solution by determining if the child subtrees contain the value that we're seeking. And then of course, do the praying that the recursive calls indeed will eventually shrink that composite problem into a base case problem. The contains tree method that we wrote is an example of a depth-first search. What is a depth-first search? Well, if you start to trace these recursive calls, when I call contains tree on line 139 here, and it goes back up to the top, and it itself is going to call contains tree and go back to the top and so forth, what we see is it's going to actually initially try to resolve all these left side branches before it actually gets around to any of these right side branches. The search is going to look all the way down the left side of the tree until there's no more left nodes, in which case it's going to step one to the right, and then try to go all the way down to the left again, and so forth until there's no more left nodes, and then go one to the right, and so forth and so forth. The outcome of this is that we're going to go as deep as possible first, down the left side of this tree. It's kind of like solving a coin maze by going as far as physically possible, rather than inching out slowly in every direction from the starting point. Wikipedia has some pretty cool examples of how depth-first search differ from breadth-first search. Okay, here's my depth-first search going. I look down all the way to the left, then I bubble back up, go down the left side again, go to the right only when I exhaust all my left side options until I've completed searching the entire tree. So in order, I start from the root, I go down 4 to the left, I shift 1 to the right, go down 4 to the left, 1 to the right, 1 to the right, as far down as possible, and then I restart. Depth-first search is in contrast to breadth-first search, which is going to walk the tree one layer at a time. This is like doing that coin maze, but inching out slowly in every direction from the starting point. Let's see a demo of how that works. Here I start out with the root node, but rather than going as far left as possible, as deep as possible, I'm going to spread out my search one layer at a time. So I start out with the root node, I examine all the nodes of the next layer, 2, 3, and 4, then I examine all the nodes of the layer after that, 5, 6, 7, and 8, and then finally I reach my leaf nodes 9 and 10. This is very much in contrast to my strategy with depth-first search, where I looked as deep in the tree as possible before percolating back up and going back down again. The key implementation difference is that depth-first search uses the stack, while breadth-first search is implemented using a queue. We will learn about the execution stack next time, and you all know what a queue is. Before I let you go, I want to mention these binary tree search strategies that are specific to binary trees. Depth-first search in a binary tree can take place in 3 ways. In-order traversal, which is traversing the left side, then the parent node, and then the right side. Pre-order traversal, which traverses the parent, then the left and the right. And post-order traversal, which traverses the left and right, and then the parent. Notice how the name of the ordering, in-order, or pre-order, or post-order, indicates the position of the parent node relative to its left and right children. One pseudocode representation of in-order searching is in-order has the parent in the middle, so I'll go search down the left side first, as deep as possible. Then when I've resolved all the left sides, I'll return the current value at the root, and then I'll search down to the right side of the tree. The clever thing about this in-order traversal is that if you think about this recursively, when I call search of root.left, the recursive call is going to come back up to the top and call root.left search again, which itself is going to call root.left search again until there's no more left side nodes. Then it's going to examine the payload at the current value, and then finally it's going to defer to the right side. But that's going to come all the way back up to the top and look down the left side again. So this version of in-order traversal that we're seeing is very much like the traversal that we saw in that Wikipedia video, where we went far down to the left side as possible, and then looked at the parent, and then went as far right as possible. I've given you a reading for this week where you can look at these tree searches in more detail. Okay, thanks for listening, and I will catch you next time.